Anyway, know these guys. I don't need you to know the formulas. I just wanted you to show off, okay? And what I do want you to know about dB is, so when this ham radio operator, and there's always one, tells you that they've been an amateur radio operator, you know, since the Marconi days and that kind of stuff, and you put up a new antenna, and he's got 20 more dB. Tell him, so what does that mean? You know, it's a ratio. That's what I really want you to know, okay? So don't let them razzle-dazzle you. I don't want anybody razzle-dazzling you guys. All right, so you really don't need to know this. One of the questions you will be asked, again, it could be any one of these four things. The most common one on 3 out of the 5 exams is 1 dB loss. Remember, minus 20.5. Okay? So that's the most common question that they're going to ask you. So don't let it stress you out here too much. That's all you need to know about this. Power ratios, there are no power ratio questions on the exam, so don't worry about it, okay? All right. And then they talk about RMS. Again, the best thing I can recommend to you is if these things freak you out, okay, then you can go to hamstudy.org, go to General, click on the flashcards, and on the upper left-hand corner, select module G as in golf 5. And it has all the 30 possible questions they can ask you. Take that over and over again. 4 or 5 times, you'll memorize the answers, okay? So, and that's the easiest way to do this, okay? So what you need to know is power is rated in different ways, okay? So they talk about peak power and peak envelope power and peak-to-peak power and all this other stuff. And one way that we measure power is RMS. And RMS stands for root mean squared. And what that is an overall average. So if you go out and buy a stereo, you know, even if it's a car stereo or a home stereo, and say this stereo's got 2 million watts. You know, how is that rated? Okay, a much more important value for a stereo is RMS value. What's the average power that it puts out? Okay, so they measure power in different ways. So we have this. If I just measure this part here, okay, if I were to look, and this is a sine wave, we're just using it as an example. If I want to measure just this part here, it's called the peak value. That's how much power am I putting out at the peak of the wave, okay? If I want to measure peak-to-peak power, it would be one complete cycle from here, and then we have to keep going. So imagine this line keeps going, right? So it keeps going up like this. And we would measure the power, we would measure the power, oops, sorry about that. We would measure the power from this point to this point, okay? So it'd be from here to here. So that's how we would measure this power. And that's called peak to peak, okay? And the reason I want you to understand the distinction is because they come up with all of these super duper formulas that are totally confusing to everybody, and they don't need to be, okay? So when they talk about converting to RMS, the value is 0.707. You can round it off to 0.7, forget the other 07. So if you want to convert peak power to RMS, okay, the way you do it is you multiply by 0.7, and that gives you the answer, okay? If you want peak-to-peak value, so from here to the other one, so from this guy, oops, sorry. So from this guy to the other guy, peak-to-peak value, you do 2 times, and that's how you get it. Again, I don't want you to stress about how we compute these things. There aren't that many questions like that. Okay?
So why would we need to know peak-to-peak versus peak versus...
Because that's what the FCC wants to know. When you're putting out power, well, no, there's a reason. The FCC measures power by peak-to-peak value. Okay? So you don't want to do... The reality of it is it's because that's the law. Okay? Does anybody really follow it? not that many people, to be honest with you. Okay,
Okay.
I'm ashamed to say. So we're limited to 1,500 watts peak-to-peak power. Okay,
Hmm.
but you know what? You'll see.
Okay. Okay.
Especially on HF, not so much on 2 meter or 70 centimeter. But again, remember those guys that live in wherever they live and they have family on Jupiter? Okay, those guys just love to be heard. So they have rows and rows and rows and rows of amplifiers, and they far exceed. Hold on, let me show you. I'll show you one. My favorite. Hold on a second. Here you go. Look at that picture. Holy cow! I mean, give me a break. You're
Oh
going to
my
tell me
God.
he's putting out 1,500 watts? Are you kidding me? Just these amplifiers alone are about probably, just this little section here is probably each one of these, and he's got 6 of them, right? So each one of these is probably 3,000 watts. And this is an
Wow.
actual station. I've spoken to this guy, okay? And he'll like destroy your radio.
Oh my God.
It's like well, you know what? People really get into it because, and I understand, because it's a lot of fun. You get to talk to a lot of different people around the world. It really is a lot of fun, and throughout the United States, and they get into it, and this is what they have. But yeah, and he's not the only one. There's a ton of people like that. So the idea here is the FCC, if they decide to snag you, they'll say, well, you're limited to 1,500 watts peak to peak, not RMS, not peak. So they don't ever want you to exceed 1,500 watts. Does that really happen? Not really. I have to be honest with you. You'll see. You'll see.
Okay.
Okay. So anyway, they give you a bunch of examples. I'm going to send everybody chapter 4 of this manual. You don't know where it came from, okay? So you can go over it in a little bit more detail. Do not, please do not stress over these formulas. I know people with extras that have no idea how to compute this, okay? And chances are, for the casual non-electronic engineer, you'll never use this, okay? Very rarely will you use it. And when you do use it, you know that it exists, so, and you'll know where to find it, okay? All right, so that's it. They'll give you, this is kind of an important one. So this, if you want to make note of that, this G5, so it's module G5B06, okay? I think it's on every exam, this test, okay? So you see oscilloscope, measures 200 volts across a 50 ohm load. The peak envelope power is, the answer is 100. So just memorize it, okay? And you'll get it right, okay? All right, so this is peak envelope power, which is another way of measuring power. And again, I'll send you this chapter so you can read it and you can certainly ask me questions, okay? They talk about one question that'll be on the exam. They'll talk about the temperature coefficient of a component. All that really means is as components get colder or warmer, their performance changes, okay? So their value, their resistance, their capacitance, their inductance changes with temperature, okay? As a general rule of thumb, the cooler it is, the more efficient they are, okay? So if your radio starts to get hot, you'll see that it's not as efficient. It's not putting out as much power, okay? All right. All right, so somebody had asked me about these resistors and capacitors. It's on your study sheet, the additional ones you need to know. They're not a lot.
Oh.
It's just a couple of little guys. Hold on, I'm on the wrong sheet. Here we go. What the heck am I doing? Oh, here. Too many monitors. Okay. So these are the additional ones you need to know. This one I taught you in the technicians class. So field effect, this is a transistor, right? Because it's got a circle, okay? It's got this straight line and an arrow hitting it directly, and it's got this little arrow shape here, as opposed to this guy. And the two leads coming out of it are parallel to each other, as opposed to this guy. Can everybody see that? So as opposed to this guy, this is what this looks like. And it's a field effect transistor, and everybody knows what the question is going to be, right? Which transistor has a gate? And you know the answer. It's field effect, because to get to the field, you have to go through the gate. They'll talk about a Zener diode, and it looks like a regular diode with this long Z thing here. Okay? And then they'll talk about the two types of transistors. And the only one they're going to ask you about is the NPN transistor, and that has this little arrow pointing out. That's how you know it's an NPN. Negative, positive, negative. That's what it stands for. The other type of transistor is positive, negative, positive. And guess which way the arrow is pointing? The opposite direction. Okay. And then they talk about a transformer, which is just two inductors with these lines in the middle of it, and a tapped inductor. Okay. That's the only other ones you need to know. And they're pretty simple. No worries. Okay. All right. Okay. Nothing more in here.
Oh, that is.
And it, yeah.
I was just going to say, is that in the book, that big page of diagrams?
Yeah.
Okay.
I'll send it over to you. I'll send it over. I'll copy chapter 4 over for you guys. And remember, you don't know where you got it, right? Okay. The ARRL would kill me. Okay. So they talk about parasitic inductance. That's on 2 of the exams. And that means that even if your radio is off, okay, it's pretty much everything in electronics still draws some power, okay? And that's the reason why if you leave batteries in something and you forget about it for a year, you come back and the batteries are all corroded and nothing works, because just having the batteries in there, even the batteries, if they're outside of the device, okay, will start to lose power, and that's because of their chemistry or because of amperage being drawn from a circuit, and that's called parasitic inductance. Okay. All right, cool. And we talked about these inductors. I showed you inductors. Anything with wire around it, anything with wire around her is an inductor. And Gloria, you know how inductors store energy, right?
Magnetic.
You're the best. You are the best. Okay, so they talk about the different types of inductors. I have another question, Gloria. On capacitors, how come people still use ceramic capacitors?
I don't know the answer to that.
Because they're cheap.
Oh,
Yeah.
okay.
That's the only and that will be a question, okay?
Okay.
Why would you use ceramic capacitors when you have all these other, because they're cheap. Okay. All right, cool. So anything with wire around it, and you can do it different ways. There's laminated core and blah, 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 and powdered iron ferrite, toroidal inductors, all big fancy words. It's just something with wire around it. Basically, that's it. Okay? All right, cool. Capacitors, no, don't touch them, okay? Be careful with them. Even the little ones will hurt you bad. That's all you need to know. We discussed how they're made, and I showed you some examples on the YouTube videos. And they talk about the ceramic one. This is the question that they will ask you. They are inexpensive. Okay? They're cheap. Okay? So your Baofeng radio that you're going to buy will have ceramic capacitors in them, as opposed to a really good, $400 walkie-talkie, and it may have, electrolytic or silvered. That's the difference. Okay, so we talked about these 2 circuits. Everybody's okay with this, right? Series circuit, parallel circuit. Series circuit, Christmas tree light. One light goes out, that's it, it's over. And then you start using words that, you wouldn't want your mother to hear. And then parallel circuits is like going to Macy's. There's a million aisles. Pick one and go down it, right? Or go to Target or whatever. Okay. Then they come up with this horrible, this is just horrible, explanation about things, okay? So they're going to ask you, everybody's going to get a question on this. It's super simple, I promise, okay? So all you have to remember that in the series circuit, okay, we add resistor and inductors, okay? Or if you want to remember it even easier, in a series circuit, The only one that's got a weird formula is capacitors, okay? And in a parallel circuit, the only one that's normal is capacitors. So in a series circuit, it's the voodoo, BS formula here that you have to 1 over something. How am I ever going to compute that? Oh my God, I did terrible in math. Super easy, okay? And in a parallel circuit, you add capacitor values. Everything else is the 1 over stuff. See this 1 over stuff? Don't let it throw you, okay? I'm going to show you how it works, okay? All right, so on this side of the fence, these are all series circuits, right? So we're going to add things together for resistance. Inductance is known as L, so we're going to add them together. The only one that's different in the series circuit is this capacitor, and you got to do all this math in your head. No, I'm only kidding. You don't have to. Okay. So you compute the value by 1 over the first capacitor, the second capacitor, the third capacitor, and that gives you the value. In a series circuit, if you want to compute the resistance of something, so if I said, let me pick on somebody. So Bob, in a series circuit, I have 3 resistors, and their values are 10, 10, and 10. What's the total resistance?
30.
You got it. Okay. Prahub, in a series circuit, I have inductors, and they have values of 5, 10, and 15. What's the total value?
30.
That's it. No harder than that. Okay? Very, very, very simple. So you just add them together. What am I going to do about this guy? Okay? Okay, very simple. What I want you to do is, I'm going to switch screens here for a second. Let's see if I can find this. Here's the calculator I told you to buy. Okay? Very simple. So let's take their example, and I'm going to show you how we compute this. Because the same thing applies for, okay. So the question is, what is the total resistance of 3 100 ohm? No, let's try something different. Okay, what is the total resistance of 300 ohm resistors in series? So since it's a series circuit, we just add them together, right? 100, 100, and 100, and we get 300. Parallel. What happens if the same question, but in parallel, okay? And this is a question on the test. How do I compute this whole mumbo-jumbo thing here? How does that work? Very simple, okay? So what you're going to do is you're going to whip out your calculator, and you're going to type in, and I'm going to try to do this way. You're going to hit, I hope you guys, can you guys see the red dot on your screen?
Yes.
Okay. So they want 3 resistors
Yes.
in parallel. So you're going to clear it, on and clear, right? And then you're going to type in 100, 100, okay? And you're going to hit this button here. See this button that says 1 over X?
Mm-hmm.
Okay? And then you're going to hit the plus, and you're going to do it again, because the second resistor in parallel is 100. 100, 1 over X, and you're going to hit the plus. And since the third resistor was 100 ohms, you're going to do it again. 100, 1 over X, right? And you're going to hit the equal sign. And then you're going to get some weird number. What do you guys get?
0.03.
All right, hit the 1 over X again. What do you get?
3.3.
33.33.
Guess what the answer is?
Mm-hmm.
Okay? So whenever you get this whole mumbo-jumbo about 1 over whatever, okay, remember that all you're going to do is you're going to hit that 1 over X. And when you get the total, hit that 1 over X again. That's where people mess up. They forget to hit the 1 over X again.
Okay.
Okay? And everybody's going to get one of these suckers. Now, the problem may be that that you may not get, you may get either, they mix it up pretty well between series and parallel, so this is the part you have to worry about. And it's on your study sheet, okay? So, and we discuss it here, right? I think it was in this formula, which I narrowed down this way. So just remember, okay, that capacitors, you add them together in a parallel circuit. Everything else is that crazy formula. Whip out your calculator. In a series circuit, capacitors are the crazy formula. That's the easiest way to remember. Okay? No biggie.
Okay.
See how easy it is? It's no big deal. Okay? Again, this is important if you're going to start building kits and stuff like that, but they want you to know it so you know it. So that's this whole section here, and they talk about all the stuff and whatever. And anyway, it's the same thing. Inductance, don't forget, is just an inductor, and it's defined here in the same thing, this inductor. So we add them together in a series circuit, and we do the crazy formula in a parallel circuit. All right? Not so bad. Very simple. Okay. So I'm going to go past all of this stuff. All right. The other thing they'd love to ask you about is transformers. And basically, transformers are nothing more than two inductors put together. Okay? And they transform things. So we have one inductor here. Can I draw or what, huh? And then they have another one in here. And since Gloria told us, and she would never lie to us, all right? Actually, let me make it simpler. Gloria would never lie to us. 1, 2, 3, 4, 5. And then here's another inductor, 1, 2, 3. So what transformers do for us, okay, is they can transfer power, okay? They can change power. So we plug those wall warts that everybody has at least 50 of in their house that converts 110 into 12 volt or 6 volt or whatever, okay? That's all that is. And the way that this happens is we're just two inductors. And since they store energy magnetically, as Gloria told us, we transfer some of the energy over and are able to manipulate it because of inductors' property of storing energy magnetically. That's why it's important. So we can convert power up and down, okay? And they have a primary winding and then a secondary winding, okay? I don't recommend that you get too crazy about this. There's only one test with one question on it. So whoever gets question 4, you're stuck with having to figure it out. Other than that, you don't need to worry about it. I'm more interested in you knowing that transformers are really just two inductors together. And they talk about this primary winding and secondary winding, okay? And there's a formula for it, which is here, okay? And they give you an example. Remember, I'm going to send you this version. So they ask you, what's the voltage across a 500-turn secondary winding if 120 volts AC is applied against a 2,250-turn primary winding? So they give you the first inductor, that's 2,250 windings, and then the secondary is 500, okay? And then using the formula of the secondary divided by the primary, okay, times the voltage, that's how you come up with this answer. Again, I'll send it to you. Don't worry about it. Only one exam. Exam number 4 has the question. I mean, it's nice for you to know how to do this and you know that they exist, okay? But don't stress over it, all right? Okay, then they talk about reactance and impedance. We have a pretty good understanding of what that is. Remember, it's the opposition of flow in a circuit, okay? And what I want you to know about it is that in a capacitor and an inductor, they both exhibit that same reactance and impedance effect, okay? And you can read about it here. There really is no major question from that, okay? So The only thing you really need to understand is the opposition to AC current. So that's the current coming from the wall, and it's stored in a capacitor is known as capacitive reactance. So what's holding that? Where is that energy going? Well, it's going into the capacitor. And then they give you this really crazy formula. I have yet to see it on any exam. Please don't worry about this, okay? If you're going to figure this out, we figure this out in the extra class, okay? The extra class is a different animal, okay? So if you take once you pass your general and you go for the extra, you know, we expect you're extras. You're the best we have to offer, so we expect you to know how to do all this stuff. But for the general, I've never seen it on the exam, on any exam, okay? I can't absolutely guarantee that it won't be on your exam because some of you live so in California, the exams are almost identical to the ones in New York. I don't know about, you know, all over the country, but so far nobody's failed, so I would assume they're pretty close, okay? All right, and then they talk about inductive reactance. Inductors also resist the flow of AC current, and then they talk about discharge and maximum current again, and they give you this other crazy formula to figure out. Don't stress about it, okay? What I do want you to know is that inductors and capacitors resist the flow of electrons in the circuit, and they handle things differently, okay? So in an inductor, the point here is, in an inductor, okay, over time, okay, the more time goes by, the greater the current increases, okay? The opposite is true of a capacitor. So capacitor starts drawing a lot of energy when you first turn it on. So when I first turn on my power supply, it takes a lot of energy, and then it starts to drop off over time. Because it's like a battery. It's getting charged, right? The inductor is the opposite of that. And that's why we have to be careful with capacitors, because they store the maximum amount of energy in the shortest amount of time. And that's why, and they discharge at a very slow rate, capacitors. That's why I want you to be careful, okay? Inductors is the opposite of that. Any questions? We are so far so good? All right, we spend 2 days in the regular general class on this, okay? So I don't want you to get too stressed. Remember, you can always go to hamstudy.org, G5, and it has all the exams. Impedance, opposition of current, okay, caused by resistance, reactance. That's all you need to know. Impedance, it impedes the flow of electrons. Think of it that way, okay? Resonance we discussed in the technician class, okay? I have to be careful because Lou's monitoring the class. I just saw him on here. And if I say tech class, he'll get really pissed off at me. So, and the technician class, resonance. Resonance is, right? Everything is working. Everything is responding correctly. And that's why we need antenna tuners for our HF radios, right? Because we're not going to go out and change the length of our antenna every time we use the VFO and change the frequency, okay? So the official definition is resonance in a circuit or antenna occurs when the capacitors and inductors, all of their values are equal. Everything is working the way it's supposed to, okay? Again, everything I tell you here is not 1,000% correct, but it's what you need to know for right now. And what I need you to know for right now is you're not going to turn on your radio. Let's say you go out and you buy one of the FT991 Yaesus for $2,000 or $1,500, or you go out and you buy a $6,000 radio and your antenna is awful, just a little tiny piece of wire, and you hit transmit and the thing smokes. That's the reason it's going to smoke, because the antenna wasn't resonant, okay? So the capacitive, the inductance was very high. The SWR was probably off the wall. Everything fed back into the radio, and you blew it up. That's the takeaway here, okay? And even if you put up an antenna and you're not reaching people that you should, okay, and they can't hear you, is because your antenna is not resonant. Something is wrong someplace. All right? That's why when Gloria said, what should I buy? And I recommended the longer antenna for the stock antenna on the Baofeng, and then if she really wants to get fancy, to hang out that magnetic mount antenna out of her window. I talk on that every night. And as a matter of fact, my wife, who's a net controller for Aries, that's what we talk on, and it works fine. Okay. So resonance. So your antenna needs to be resonant. You can do that. You can do that physically by shortening or lengthening the antenna, or once you do that once or twice and that gets old really, really quick, you go out and you buy an antenna tuner. Antenna tuners are not needed for 2 meter and 70 centimeter, okay? Not generally. You have to worry about the SWR more than anything. And remember that if the SWR exceeds 2 to 1, so for every 2 watts you're putting out from the radio, 1 watt comes back into the radio, that reflected power. If you keep doing that for more than a few minutes, the radio itself will shut down. It'll just stop working, shut itself off. Okay, it's built in. All right, cool. And then they come up with these totally inappropriate formulas, but it's their rodeo. Impedance transformation. They want you to. There are no questions at all on this. Okay, nobody's going to figure this out. It's not happening. Okay, so there are no questions here about this. Again, if you want to learn about it, I'll send you this, and you can figure this out. Okay. Impedance matching. Okay, it's my antenna tuner. Remember I showed you that? I pressed a button and it made all this noise, and then it matched. My antenna length doesn't change physically, and I changed it by using inductors and capacitors in this little unit you buy for about $100, anywhere from $100 to $200. You slap it onto your radio. You take the output where the antenna would go, you plug it into this circuit, okay, and the antenna hooks up on the other side. When you want to match the antenna, you press the button, off it goes. There's manual ones you can buy. Just Google antenna tuner, and you'll see a bunch of them. And what's important that you need to know is they're known as pi networks for your purposes. They're known as pi networks, they're known as T networks, they're known as LC circuits, L standing for inductors, C standing for capacitor. That's why they're called LC circuits, okay? Hey, look, they're made out of inductors and capacitors. Hence the name, LC circuits, okay? And there are a whole bunch of, different names. You can tank circuits, they're known as. And what they do is they allow the maximum amount of power to be transmitted from your radio to the antenna, and they make your antenna resonant. Okay? So you don't have to go out and start snipping wires. All right? That's their main function in life. All right? All right. Semiconductor components. All right? So all you need to know about semiconductor components is transistors are one of them. Okay, there's a bunch of different types of transistors, and then they talk about whether they're NPN or PNP transformers. Okay, and the only one you need to worry about, as per my notes, is this guy, NPN, and that's because this little guy right here is pointing out. Okay, and if it was a PNP transformer transistor, it would look the same, but pointing in the opposite direction. That transistor has two functions in life. Dana, what is a transistor's 2 functions in life?
To switch or amplify?
That's it. That's all they do. Okay. You'll find that that's not quite exactly true when you go to your extra, but for right now, perfect. Okay. Guaranteed. Double your money back. Okay. I promise you will get this question on your exam. Okay, diodes. Remember diodes, Roach Motel, electrons go in, but they don't come out in the same way, okay? And that's why if you look at the notes, they're here. Why you would need to know this at this juncture of your life, I have no idea. But it's their rodeo, so we will go by their rules. So this one, take it to the bank. It will be on your exam. Okay? All right, cool. And they talk about these other things, peak inverse voltage, average forward current, not on the exam. And they're talking about how diodes work, okay, and what they really do and how they work, okay. And they talk about these bands here, and that's how you rate rate a diode. So diodes have different values, and that's basically it. Nothing. And they talk about all these other different types of diodes. The only one that will be on your exam is the Zener diode. It looks like that regular diode with the Z, okay? And they're used for switching, okay? They're used in power supplies a lot, okay? That's their job, okay? Bipolar and field effect transistors, all you need to know is, hey, here's a PNP transistor. The arrow's going in the opposite direction. So, so the way I remembered it was PN points north. So make believe that's north. Okay. So if it points in, it's PNP. If it points out, it's NPN. All right. And transistors have no charge in and of themselves. It's what they allow. Okay. So they allow positive particles to pass through. Okay. They're PNP. And if they allow negative particles to go through, they're NPN. So it's just what we allow. Okay. But they themselves have no value, positive or negative. Okay. All right, cool. Vacuum tubes, everybody knows what they look like, right? And they may ask you a question. I think one exam has a question on it, and they want to know what the source of electrons in a tube is, and that's the cathode. That's where the electrons come from. So the way a tube works is there's a bunch, it's a glass structure, there's a plate, there's a collector, and there's a heater. So again, it's that thermal variations. Tubes have to heat up before they work efficiently. And the cathode produces the electrons, okay, and what collects the electrons is called the plate. Not really on, it's only on one exam, and not so important. Okay. Then they talk about integrated circuits. Anybody know what an integrated circuit is? Anybody want to give me a guess?
Computer on a chip.
Yeah, it's like a gazillion transistors. Okay. So you take like a bazillion transistors and you slap them on one chip, and that's an integrated circuit. Yeah, it's not really a gazillion, bazillion. They could be thousands, they could be millions of transistors on a single chip. And everybody knows what a computer chip looks like, right? They're really tiny. And that's what they are. Okay? All right, and they talk about analog and digital integrated circuits. So the beautiful part of having all these gazillions of transistors in here is that they can make a judgment. Okay? Yes or no. Okay? Yes, I'll let you pass. No, I won't let you pass. Okay? And the way that's done is through logic circuits. Okay? And I define the ones that you need to know in on the sheet. Okay? And these are the only ones that are on the exam that I know of. Okay? So they're gates. Think of them as gatekeepers. So here, okay, they won't ask you for these symbols or any of that stuff. So a circuit could be either on or off. There's no in between, right? Forgive the analogy, but it's like being pregnant, right? So you either are or you're not. So there's no in between. So if we have off is equals to 0 and 1 is equals to on, so this is what we call the truth table. Okay? And that's how we evaluate things. Now this is an AND gate. Okay? This is an AND gate. So in an AND gate, the only time it'll let something pass is if the first part of the circuit is on and the second part of the circuit is on inside the integrated circuit. Then it'll let it pass. Any other value it won't let it pass. The ones you need to know are here. Okay? So what's going into those integrated circuit is the input. Okay? And we evaluate that the output is high or on only when both inputs are high. The NOR gate pretty much is a little bit opposite of that. The output is low when either or both inputs are high. Right? Those are the two major logic circuits. Yes, go ahead.
How does, I'm trying to figure out how that makes sense. It says the AND gate, the output is high when both are high, but again under NOR gate you also list that both are high.
Yeah, so the output is high, all right, so go for it, all right, so it's full blast, okay, when both inputs are high. NOR gate, the output is low. Not off, but it's much lower when both are high. Why do we use that? We use that, for example, to restrict voltage.
Okay,
so if we just had a bunch of inductors in a transformer, okay, and we didn't have a logic circuit controlling that, man, we could like nuke the planet. So you put this logic circuit in, okay? So the difference is NOR output is low. And that's an easy way to remember the question, okay? So the question will be, where is the output low? And they'll list all of these things that nobody knows about. NAND gate and OR gates and NOR gates, and there's more, inverters. And the answer is the output is low when you have a NOR gate, okay? And again, the question will read, both inputs are high, when is the output low? NOR, okay? The inputs are high and the output is high. It's an AND gate. Okay, and what they're trying to explain to you here is, again, remember that this course is designed for people to generally get into radio. You have a little bit of knowledge. We don't want you blowing up China, right? So we don't want you to cause a fire. You're not going to blow up China, but we don't want you to get into trouble. Okay, so you need, the point is that you need a logic circuit in here. All right, don't worry about these other things, not on the exam at all. Okay. All right, cool. Then they talk about other circuits like flip-flop circuits and that kind of, and clocks and that kind of stuff. You can read about it, not really on the exam. Don't worry about it. And integrated circuit. The most popular one is MMIC, monolithic microwave integrated circuit. Okay, and that's what makes your microwave oven possible. Okay, and what it does, it's actually an interesting device. It'll take RF signals, okay, it'll combine them together, and it'll work through all the way up to microwave frequencies. And every microwave oven has an MMIC integrated circuit in it. Okay. All right. Memory. Everybody's pretty familiar with computers, right? So we all know about RAM, random access memory, dynamic RAM, DRAM, okay? ROM, R-O-M, read-only memory, EEPROM. Everybody knows the difference between RAM and ROM. So RAM is what pisses you off when you get a power hit. You're typing this fantastic, you're writing the great American novel, right? And all of a sudden, the power goes out. And you didn't save the file, right? And everybody gets really upset. Why? Because as you're typing, if you don't save the file, that's stored in RAM, random access memory. So it's volatile. So if you remove power from the circuit, that goes away, okay? ROM is when you first start up your computer, Computers are incredibly stupid devices, okay? Computer circuitry works basically the same. So how does your computer know it's an Apple or it's an IBM or a PC? Well, because of ROM, okay? Its basic operating, or what it is, its consciousness, if you will, if I can take a little poetic license, is ROM. It's always there, ROM. Like game cartridges that you use remember the old-fashioned game cartridges that you used to have to buy for like 60 bucks and you pop it into your machine? That's ROM. Okay, it's always there. Power goes out, the game is still there. Okay. All right. Any questions? Are we good? We're almost done, I promise. Okay. And everybody familiar with computer connections, right? I don't think they use most of these anymore. The only one that's still used is FireWire. Okay. And you can see how dated this book is. They're up to USB version 3. And that's how when you plug in your mouse or your keyboard or something, that little flat thing, that's USB. They had other versions of that. The predecessor of that was RS-232 in the old days. And then Apple innovated FireWire. And it's how fast they transfer data. Okay? The old-fashioned printers used to use parallel printers. And how your computer talks to its hard drive is ID888. But again, they won't ask you about this too much, okay? They will ask you about random access memory, okay? And they'll ask you about ROM. So they'll say the power goes out and your radio comes back up. Why is that? Because it's in ROM, okay? So for example, does everybody got that? Do I need to discuss that further? Are you guys okay with all of that?
Mm-hmm.
Yes? No?
Yes.
Yeah. Gloria, you good with this? I guess so. She didn't say no. Bob, you good with this? No problem?
Yeah, yeah, pretty much so.
Yeah.
I'm sure
no worries, right? Okay.
Yeah, it's okay.
Yeah, all right. So, the example I always cite is, okay, my radio was off, right? I'm just turning it on right now, okay? And I go to Ham Radio Deluxe, and now, so my radio was in a powered off state, right? And I'm going to connect, and then these are the memories that I have. So this is our repeater here in New York, okay? And here are more channels. And as I turn the channel selector, they go to different things, right? How does it remember that? How does it know that it was there? Well, because this information is stored in the radio's ROM, read-only memory, okay? So it's not power dependent. That's kind of a crude example. There's a little bit more to it than that. Actually, it's not. Actually, it's RAM, but I won't tell you. All right, think of that, okay? All right, cool. They talk about network connections and Ethernet and all of that stuff. No questions on any of that. All right. Visual interfaces. The most popular one being light-emitting diode and liquid crystal display. The question will be, okay, what's the problem with LCDs? The problem with LCDs is that you need ambient or backlight. Perfect example is the calculator we just worked on. Okay? Okay, Gloria, good. As long as you understood it, you're fine. So the calculator we're working on is an LCD. So if we turned out all the lights, guess what? Doesn't matter what you put in there, you wouldn't be able to see it. Your television is probably LED now. Used to be LCD with a backlight, but now more and more televisions are light-emitting diodes. Okay? And remember, light-emitting diodes is just a diode that is forward biased. What does that mean? It releases electrons, and that's how we see television. Okay? Then they talk about rectifiers and power supplies and blah, 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 and all you need to know is we convert it from one type to another, and rectifier circuits, okay, it makes a change in waveform. So what a rectifier does, first it goes to a transformer, then a rectifier does, think of it as it kind of smooths things out, okay? And there are half-wave rectifiers and full-wave rectifiers, okay? And it just makes everything equal. So you get those nice, pretty sine waves. That's what they do. And there's equal duration between the pulses when no current flows, blah, 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 okay? So what rectifiers really do is they just make sure everything is nice and pretty and neat, okay? That's all that this means for our purposes. You'll get into it a little bit more, again, if you take the extra class, okay? And they discuss it and that kind of stuff. And they talk about diodes and parallels and series. Don't stress over this at all, okay? Don't worry about it, okay? You can read about it and have that kind of, and play with it there. And then they talk about rectifier diode voltage and current. They have number of diodes. So in a rectifier, a smoothing out, if you will, that's a very broad definition. We also use diodes because they have a smoothing effect as well, as do capacitors, by the way. Okay, capacitors tend to smooth things out too. That's all that this means. And you get into a very heavy-duty understanding of it. And then power supply, guys, if you get that one wrong, okay, then you have nobody to blame but yourself. So the answer is that you're going to wait a long time before sticking your hand in a power supply. Why? Because of the capacitors. Okay. All right, and then they go into how this works. And the switching mode power supplies. Perfect example of a switching mode power supply is what's in your computer. All right, so a computer runs on different voltages. So the motherboard operates at 12 volts. I'm sorry, at 5 volts. The fan that cools down your computer operates at 12 volts. There's all sorts of different voltages depending on if you have a laptop or a desktop. And this explains how this is done. Okay, batteries and chargers. This is kind of common sense. Be careful what you do with batteries. Okay, don't charge nickel-cadmium batteries. Does everybody understand the difference in chemistry? I shouldn't say that. All right, let me just go over it real quick. Okay, so this chart here describes the different types of batteries that there are. One of the questions that they love to ask you is nickel-cadmium battery, a AA nickel-cadmium battery, produces 1.2 volts as opposed to a regular Duracell. It produces 1.5 volts. Okay, but the difference in voltage is so little that most things don't really care about it. Okay, and what they want you to know is never try to recharge an alkaline battery. You'll set fire to the dog. Okay, never try to recharge nickel-cadmium batteries in an alkaline charger. Okay, even though they make them, you'll set fire to the dog. Okay, and then they want you to be extremely careful with lithium-ion batteries. Okay, Google or go to YouTube and type in lithium battery explosions. So even a tiny little cell, you know, like something you put in a toy helicopter or a toy airplane, if you don't charge them the right way, okay, they will cause a massive explosion and set fire to whatever's around, okay? The question you will be asked, okay, is why do you have to be careful when you're charging or discharging a lead-acid battery, i.e. the battery in your car, okay? The answer, because it produces hydrogen gas, and it's explosive. Here's the question right here, and the last part of this. For example, lead-acid batteries aren't sealed give off explosion hydrogen gas during their recharging and discharging, and should always be recharged in a well-ventilated area. That will be on your exam. Okay. And even if they are sealed, they still emit hydrogen gas. Okay. They talk about alternate power, and you can read about that. Again, they use different types of transistors along with silicon. they use the power of the sun. I think I explained this to everybody in the technician class, right? So the way, you know those lights that they have for your garden? You know, ever see those? They sell them like at Home Depot.
The solar lights? Yeah.
Yeah, solar light, right?
Mm-hmm.
Listen, man, we have about 500 of them in our house, okay? My wife, she has this thing for them, okay? All right, so anyway, the way they work is they've got the solar cell here, right? And the sun beats down on this bad boy, okay? And it's silicone and a couple of transistors inside this thing, and it converts the solar energy into electricity. But what's inside of this guy is a diode, okay? And that diode, so inside there's a diode, okay? And that diode is charging a battery, like a AA battery. Take one apart, you'll see, okay? And then that battery also lights up the light. So we have the bulb here. Man, I can really draw, can I? All right. All right. So why is this diode here important? The diode's important because remember it's what it does. Electrons only flow one way, right? So everything is cool when the sun is shining. But when it gets dark, if we didn't have this diode in here, the power would go from the battery, and instead of lighting this light, we'd go back up to the cell and out the window. It'll dissipate that as energy, as heat. That's why they have diodes in them. Okay? And the reason I know is because they were giving me a hard time, and I took about 10 of them apart. Okay? That's how I know it so well. All right, anyway. Talk about storage batteries. We already talked about connectors, right, in the technician class. And there's a connector for everything. There's PL259. There's N connectors. And you'll get a connector question in there. And again, here's the famous connectors and power strips and binding posts and all the cool things you get to play with. There isn't really any questions on connectors so much, okay, other than they want you to know which connector is waterproof, okay, and I'll let you figure that out because I already gave you that answer 6 times. All right, cool. And here's more connectors, and there's ring and fork connectors, blah, 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 okay. Miniature phone plugs. I have this huge box just filled with connectors, okay. So there's 3 things in life you can never have enough of: love, money, and connectors, okay, in that order.
Antennas.
So especially, excuse me?
Antennas.
Yeah, you're right on that.
4 things.
Well, I don't change my antennas as many times as I change my connectors. So anyway, you'll see. If you stay in this hobby for a while, you will have that same box that I have with every connector that you have no idea what to do with, but you gotta have it, okay? So, and adapters, and mono to stereo, and stereo to mono, and oh my God. That's why Radio Shack took so long to get out of business, because people were buying all these connectors, okay? RF connectors, we talked about them. Same diagram as in the technician class. And we have SMA and N connectors and B and Cs and PL259s, and okay, just know that they exist. Okay, that's all I need you to know. All right. So for example, if you buy a Baofeng, you got to buy one of these. If you don't buy that antenna that I suggested Gloria buy, you need to buy one of these. Okay. Because everything is PL259, a regular antenna is PL259, but then your Baofeng uses SMA connectors and whatever. All right, cool. And then basic test equipment, we know what that is, ohm meter. So you should definitely buy one, read the instructions. Actually, there's a great YouTube video on how to use an ohm meter. It slices, it dices, it makes julienne fries, it'll make great tea, it'll babysit the kids. Whatever you need it to do, it will do. It's the single most useful piece of information, tool that you have. And now they're so advanced, they have battery testers in them, and they have impedance checkers, and they have all sorts of stuff for like 20 bucks, okay? So pretty cool, okay? Oscilloscope, okay? Oscilloscope measures a wave, okay, in a moment in time. what the wave is doing, what the circuit is doing, okay, is extremely precise, all right? So it can take any waveform, you can press a button and freeze it in time, and it's incredibly accurate. And that will be the question, okay? So the question is this one, okay? Enables technicians to observe complex, fast-changing waveforms that beyond the abilities of meters to measure. This device, the multimeter, will measure waveforms as well, but it's very difficult to keep a track of, and you can't see what happens in between because it happens so fast. The oscilloscope freezes the waveform in a moment in time, okay? As a matter of fact, my oscilloscope will measure up to 22 hours, and I can play back the waves for 22 hours. So if you have trouble going to sleep at night, buy yourself an oscilloscope, measure anything for 22 hours, and you'll see that it'll put you right to sleep. Why is that important? Remember that what we discussed about that thermal coefficient? So as things heat up and as they cool down, they react differently, okay? That's a great way to find out what the wave is doing over time. Capacitors, it'll measure capacitors. How are they discharging over time? Every capacitor has a different discharge time, okay? So they're really a very, very, very precise. Remember that question, you will get it, okay? All right, and you can measure, everything in life is in sine waves, so you can measure transmitter output, you can measure all sorts of stuff, and then when you want an oscilloscope that's specifically for radio, okay, they make one like that, and then be ready to spend some serious money on that. But anyway, that's what oscilloscopes do, okay? And they're used for diagnostic tools. When you get a schematic, a very detailed schematic, what they'll do is they'll say, okay, everybody knows what an oscilloscope looks like, right? So it has two probes, right? And it'll tell you to measure from one place to another, and they'll say the wave needs to look like this. And that's how you tell if that component is bad. And they actually draw a little diagram, and they say, okay, this is what the wave looks like. And if the wave doesn't look like that, then you know that's the component that's bad. I'm oversimplifying it a little bit, okay? But generally, that's the idea, okay? And signal generators, sometimes we haven't got anybody to talk to, and we need to fix our radio. So we have these signal generators, all right? And they simulate CW, AM broadcast, FM broadcast, all sorts of cool stuff. I have a little tiny one, but you know the big heavy-duty ones are pretty cool. And then impedance and resonance measurement. Here's our friend, the antenna analyzer. I showed you mine. Okay, mine is not quite as so many doodads as this, but mine's you plug it in there, it'll measure impedance, it'll measure SWR, it'll tell you where the antenna is resonant. Everybody remember that, right? So when the graph is at its lowest on mine, that's where the antenna is resonant. Okay. Field strength and power meters. So these are pretty cool. They're actually pretty inexpensive. This one is that we're looking at right now. What you do is, if you're just not getting through, you buy one of these doodads, you climb up on a ladder, get to the top of your antenna, hold this right by the antenna, and it'll tell you how much power you're putting out at the antenna. Not something I suggest that you do for an extended period of time, but that's what it will do, okay? So it'll tell you field strength. It'll tell you directionally, right? So if you take your antenna, you put it on the ground, use this device, you walk around it, all right, 360 degrees around it, it'll tell you in what direction the antenna is operating most efficiently, what its radiation pattern is, okay? That's what it does, field strength meter. And then you can use it for other things. We call them bunny hunts, right? So somebody goes out and puts up a signal generator, and it's transmitting at a specific frequency, and our job is to go out and find it. Not my job, okay? But anyway, they go out and basically they use a type of field strength meter, and either walking away or pointing it in a certain direction, you can triangulate where the signal is, and again, they're called bunny hunts. Just bunny hunts, right, Lou? I don't know if Lou's still, yeah, Lou's here. He's playing Lou. It's still bunny hunt, right? He's going to text me. Just want to make sure I get the right nomenclature. Okay, and then the other coolest, most fantastic watt meter on the planet, the most accurate, this is known as a BIRD, B-I-R-D, okay? Extremely precise. It's a very old instrument, extremely precise. And it takes these little, this looks like those things you put in your coffee. That's exactly what they look like, these guys, these modules, okay? They look like the Keurig coffee things, but they're not. They're much more expensive. And what you do is, depending on the frequency that you want, these come out, and you plug one of these suckers in. So it comes out, you take these guys and you plug them in here. That's a terrible color. So you take it and you plug it in here, and then this sucker will tell you exactly where your antenna, how much your antenna is putting out. You hook up your radio to one side here, you hook up your antenna to the other, and it tells you exactly what's happening. Expensive, really expensive. I don't remember what they go for, but I know that they're big bucks, okay? And that's to measure the efficiency of your rig. Because ham radio operators, they want to make sure, the question you'll be asked most often than anything is, how are you reading me? Don't forget that 5x9, right? 5x9. So your signal is good and you sound great, and it's subjective, of course, but everyone wants to know how you're reading them. And this is a device that you use to ensure that your radio is working efficiently. That's it. That's all I got. Any questions?
No.
All right. That wasn't too bad, right?
Right.
All right. Cool. 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 All right. Anybody have any questions on anything, either on the technician or on the general stuff that you need to know about?
How do you know?
Generals, yeah, go ahead.
Sorry. How do you know if we pass or fail? Do we let you know?
You're going to let me know because you love me, and I spent all this time with you, and you're not just going to leave me hanging, right?
All right.
Besides, you're going to be so excited when you pass that I'm sure you'll probably go to your next door neighbor who has no idea what amateur radio, how to even spell it, and you'll say, I passed my test, I passed my technician, and then, okay, and then she'll back away from you carefully, and won't know what the hell you're talking about. So you want to share that. So yes, I definitely want to know how you did.
All right.
Okay. It's also a measure that I did a good job, or I didn't do a good job, or I missed something. If anybody has a question on any of this stuff, okay, please feel free to email me. I'll even be happy to have a one-on-one conversation with you to go over some stuff. All right. So again, don't get stressed out on the general too much. Take the technician, get your call sign. Remember, you can get on around the world by using Echolink. Okay, it's not really HF, but you'll be able to talk to people all over the world. See how you like it. Minimal investment on your first rig. Definitely look into Aries. I can't encourage you enough. And also look up TrafficNet in your area. So in case, heaven forbid, you have an emergency, you know how to get messages in and out of where you are. I recommend everybody buy a Baofeng for 25 bucks. So even if you buy something heavy duty, have a Baofeng. In case something happens, always leave it charged. If you need to get out, that's how you can get out. Remember, I live in New York. Nothing bad could ever happen, and we had no power for 3 weeks. A couple of years ago, 3 years ago. So be careful. All right.
Joe,
thank you very much.
Can I ask a question?
Sure.
You talked mainly about Chapter 4 here, but how much on the test is from the other chapters as well?
What you really need to know, so my advice here is, this is not a substitute for a regular extra class. Mm-hmm. The only reason I suggest it is twofold. Number one is about 70%, 60 to 70% of the questions they will ask you are also on the technician class. Okay, so you're learning it now. You might as well learn it later. You know, you might as well say it twice. Okay, so they're going to ask you about dBs. All right, and you already know. You need to know that for the technician. So it's very close. You know about data modes, for example. You know that really uses 5-bit Bordeaux code, or you should know it for your technician. Okay. So the questions are very similar. Even if you don't study at all for the general, you'll probably get 15 to 17 to 20 questions correct out of a possible 27. All right. You need to know about this stuff anyway, about the different layers, propagation, and how that works. Okay. So, and you need to know, basic, QRN, QRP, QRS. So the questions are not that much more different. So I don't recommend this as being the end of your general, even if you pass. I strongly suggest that you buy the manual, and then again, if you, instead of taking a sleeping pill, you can't sleep at night, read that for a while. Anyway, but in all seriousness, you should know about, it goes into more detail. So if you know what's on this sheet, on this 2-page sheet, and you understand it, okay, and you can Google a lot of that stuff, you have a very good chance of passing. I recommend you buy the manual as well, and have it just as a reference, okay? The reason is, and stay where you are for a little while, okay? And then once you really start to understand it and the practicality of it, so now with your general, you can go on HF. And they have virtual HF receivers on the web. You don't have to spend any money on radios. You can also do it off of your computer, get that experience. Then if you want to go for your extra, you can do that. So I hope that was a long-winded answer. The answer is a lot of the questions are the same, just a little bit more in depth. That's why that's why we did this. A lot of you were technically advanced, so. And you were acing everything. I figured I'd give you the challenge, and it's free. Okay?
All right.
All right, guys, please let me know how you make out on both exams if you decide to take both. And if you just decide to take the technician, that's absolutely cool. After the first of the year, I will be giving a general class. It'll be mainly my club people that are looking to upgrade their licenses, but you're always more than welcome. Check on the ARRL site, I would say in 2 to 3 weeks, and we'll have an idea of when we're going to run the general and the extra class. Please let me know how you did, okay?
Okay.
That was the deal.
All
right, guys.
Thank you very much.
Thank you.
Thank you.
Good luck to everybody. All right?
Thanks.
Thank you.
Thank you.
Take care. Have a good holiday, by the way. I will
Thank
speak
you.
with
You
All
too.
right,
You
bye.
as well.
All right, thanks. Bye.
Good luck, everybody.
Bye.
Thank you too.